Well, welcome to this first video in the confidence interval mastery section here. I gotta say, I feel like reading the OpenText, the OpenStack text, reading the lectures is probably the hard way to go here for you with regard to learning these new concepts associated with confidence intervals, just because they're a little bit subtle. The definition of the confidence interval is a little tough to get. It doesn't help that you see it kind of written down improperly in many texts. So along those lines, I think that this mastery section might be your best bet with regard to how to learn this. I'm not going to argue that too strongly because I don't know that it's the case, but if nothing else, it explains why I've made this mastery section a little bit more involved than I have made the prior sections. So let's get going, and we're starting right away with two problems that we can do here that are as basic as it gets, calculating z-values and t-values. Z-values for normal distributions, t-values for the student t-distribution. The procedure goes pretty much the same way with small changes between those two. So first of all, why the z-value? Because I got to tell you, when you calculate or construct a confidence interval with your calculator, you'll skip right over this step. The calculator will handle the calculation of the z-value for you, or the t-value for you. However, we first ran into these critical values last week. We'll run into them in a big way in the next couple of weeks. You're going to end up calculating quite a few of these, so it's a good idea to get this under your belt as soon as possible. A critical value, I like to call them lines in the sand. They are lines, essentially lines on the distribution that separates regions of the distribution that are in some sense close to the mean value from regions in the distribution that are not close, usual from unusual, lines in the sand. So let's take on the first problem here and see how that goes. So problem one has to calculate a z-value, so that's telling you that, that you're using a normal distribution. The nomenclature says z sub alpha over 2. We'll see where that comes from in just a second. And in this case, they want you to calculate that for 79% confidence level. And the 79% confidence level is denoted as 1 minus alpha. This is the confidence level. Yeah, and if that's the case, if 1 minus alpha is 79%, then alpha is 0.21. You can just do that subtraction real quick. So let's see where that comes in. So let me draw a normal distribution. Yeah, and let me kind of show that region in the center that contains 79% or 0.079 of all the data. Right, I've done this schematically very quickly. If 0.79%, or sorry, if 0.79 falls, or 79% falls in this region, then 21% falls outside. And if indeed this thing is symmetric, then half of 21%, or 10.5%, or 0.105, falls over here, and another 0.105 falls over here. What this problem is asking you to do is to find these values which separate this area from minus infinity up to this value, which contains 0.105 from this area. And that is the value that we're looking for here, z alpha over 2. And how do you find it? Let your calculator do the work for you. You go second, distribution. The operator that we're looking for is inverse norm. And what goes into inverse norm is the area that we're looking for, 0.105, the mu, 0, and the standard deviation. So how do I know that? Because we're dealing with the standard normal distribution. And the standard normal distribution has got a mu of 0, and it has a sigma of 1. All right, so if I load the calculator with this, tell it to go, it is going to spit back this z alpha over 2 value. Note you've got, because of symmetry, you've got a positive value here and a negative value here. There will come a time when we're very concerned about the sign, which one of these two we're looking at. But for now, anytime you calculate a critical value, you're going to calculate the positive value. So I'm turning the calculator on. I am going to second distribution. I'm skipping down to inverse norm. It's asking me for the area, 0.105. It already has 0 and 1 loaded. And so I tell it to go, and it actually tells me minus 1.25, but as I've said, 1.25 is the answer that we're looking for here. Okay, without stopping, let's go do problem 2 here. Here comes problem 2. Problem 2 looks for a t alpha over 2. Therefore, we're going to associate ourselves with the student t distribution. And that's for the case where the sample size is 21 and the confidence level is 90%. All right, very much the same thing. Instead of dealing with the normal distribution, we're dealing with the student t distribution, which for large N is virtually identical to the normal distribution. As N decreases, the student t distribution, remember, is a little flatter and wider. There's a little bit more area out in the wings. And so let's just go ahead and do the exact same thing we did before, only for the student t. So in this case, I'm going to go second. I'm going to go to distribution, but rather going down to inverse norm, I'm going to go to inverse t. Okay, and whereas this looked for area, mu, and sigma, this argument is a little different. It is going to look for area and degrees of freedom. And degrees of freedom are simply n minus 1. Okay, so if that's the case, I'm 90% in the center. I'm 10% outside. I'm 5% in each wing. So the area that I'm going to enter here is 5%. The degrees of freedom, n minus 1, is 20. And all I have to do is again go to second distribution, inverse t, area is 0.05, the degrees of freedom is 20. My calculator needs to have me tell it to paste and ask it to calculate, and you'll get t alpha over 2 is equal. Again, it returns the minus sign because that's the way these inverse norms work, but I'm really interested in just the absolute value, and that is 1.7247 or 25. Okay, easy enough, they all go just like that. Let's move on to the next topic.